Everybody, so this is going to be our third lecture for chapter 16, and here we're going to look at the Doppler effect, which is going to be a concept that's going to be important for sonography students. So first, let's just start off with a speaker, and a speaker sending out sound waves. But I'm going to play a simulation to get a better idea of what this is going to look like. And while that's loading, I'm going to redraw this picture here. I'm going to get rid of the speaker and only look at the source coming out of the speaker here. All right. So here you have water droplets falling into a pool, and let's look at it from the side. So from the side, you see the water level going up and down and the wave traveling outwards. And if we look at it from the top again, you see that it forms these concentric circles. The tops of the wave, they correspond to the blue regions, and the bottoms of the wave correspond to the black regions. And let's look at the same thing for the sound wave. So you have a speaker sending out these sound waves. You get these concentric circles, and the tops of the waves correspond to the white areas, and the bottoms of the wave correspond to the black areas. So now let's go back. So I'm going to just redraw this here. You have a stationary speaker. It's vibrating and it's sending out these sound waves, and the sound waves travel out in concentric circles. And let's say that there's two people, one person standing in front and one person standing behind. So the first thing is that the velocity of the sound wave of the speaker or the source is going to be 0, and the speaker is going to vibrate with a frequency which I'm going to call F source. So there's going to be two people. What are they going to observe? So the person in front, what they're going to observe is the wavelength or the frequency of the wave is going to correspond to the distance between these two circles here. So they're going to observe a frequency received, which, let's say, is going to be 1. And the person back here, once the wave passes by, they're going to observe a frequency that's going to correspond to the separation between the two concentric circles. But since that distance is the same, they're going to observe the same frequency also. So their received frequency is also going to be 1. And that wave is going to travel towards them with the velocity v wave in both directions. So now let's look at the other case then. If the speaker is moving along with the wave. So let's say that you have a line here, and the speaker is originally here, and the speaker is moving as time goes by. And at each point, the speaker sends a pulse. So initially, the speaker is going to send a pulse, and by the time the speaker gets to this location here, the pulse is going to travel outwards. So the pulse is going to become about this big. So now, as the wave is and the wave is going to travel with the velocity v wave. But as the wave is moving, the speaker is also moving. So by the time the speaker moves to this location here, so let's say to this location, the speaker is moving with the velocity, I'll say v source or v speaker. And it sends out a new wave here. And here, if you notice, if there's two people standing, one in front and one behind, they're going to observe something different here. So if there's a person standing in front, what they're going to observe for the wavelength is again going to be the difference or the distance between the two circles. So here this is going to be a small distance. So that's going to correspond to a small wavelength or a high frequency. And if somebody's standing in the back, so over here, so this isn't a perfect drawing, but I'll just erase the main things here. So from there, the wavelength that they're going to notice is going to be this distance here. And let's pretend that the circle was right behind the person there. So the wavelength that they're going to notice is going to be a lot bigger. I'll do it in a different color. So they're going to notice this distance here. So this distance is a lot bigger. So that's going to be a bigger wavelength, or it's going to be a smaller frequency. So here, just because the speaker is moving, two people are going to notice two different frequencies. And the equation is going to be represented in two different forms. So here, this is the wave approaching. And for this person, the wave is moving away, so this is the wave receding, or I'll just say moving away. In the case when the wave is approaching you, what you're going to notice, or the frequency that you're going to notice, is going to be the received frequency, is going to be the frequency from the speaker or the source or the sound wave, and multiplied by the velocity of the wave, and then divided by the velocity of the wave minus the velocity of the speaker. And if the wave is moving away from you, and in that case, the frequency that you're going to notice, or the received frequency, is going to be the frequency of the speaker or the source, multiplied by the velocity of the sound wave, divided by the velocity of the sound wave, but now plus the velocity of the speaker or the source. So let's look at an example of this. So here I'm going to try to set the velocity of the speaker to 0 first. Okay, and now I'm going to start it. So the speaker is stationary, and you notice the circles are concentric in front of the sound wave and behind this, in front of the source and behind the source. And now let's make the speaker move. So now you notice that the waves are compressed in front of the speaker at a higher frequency, and as the wave passes by the observer, the wavelengths get longer and the frequency is going to get smaller. There's a YouTube video here that I recommend that you look at. The sound is not going to play, but it's of a car passing by you on a highway, or on the middle of a road. So here, these are going to be some applications, and let me just get rid of these notes here. This is just a review of what we just talked about. So if the siren is going to represent the source, so the velocity of the siren is going to be stationary, it's not moving, and it's going to send out a sound wave with a frequency F source. And since these two people are stationary, they're both going to receive the same frequency. So FR is going to be the same for both of them. But now in this case here, the person inside the car and inside this the fire truck, they're going to hear the same frequency. That's going to be the frequency of the source. But now, because the siren is moving with the velocity V source, the person in front of the siren is going to hear the frequency defined by this equation. Frequency received is going to be frequency source multiplied by the velocity of the sound wave, because again, the sound wave itself is moving with the velocity, divided by the velocity of the sound wave minus the velocity of the source, or the velocity of the siren. And the person standing back here, what they're going to receive is going to be the velocity, the frequency of the source multiplied by the velocity of the sound wave, divided by the velocity of the sound wave, but plus the velocity of the siren or the source. And so these are examples of animals that use the Doppler effect to echolocate objects, like bats use that, dolphins, and even submarines use that. So we're going to stop here for the lecture on the Doppler effect, and we're going to continue on with another video.